Alright, so we're covering the normal distribution on page 16 of your notes, girls. First of all, let's think about the shape. Okay, we're familiar with the shape. We're going to put the mean in the centre, and I'm going to use the letter mu, which is a U with a long tail in the front, and that denotes our population median. Our population mean. We're then going to add on the standard deviation. Now, if we remember, our standard deviation is the amount of spread from the centre. And again, I'm using the sigma, which is an O with a little tail on the top. That denotes our population standard deviation. And I'm going to call this distribution X. Okay, so this can represent any data that we have. And I'm going to write that as X is approximately normal, and then in brackets I'm going to put the two parameters, the mean and standard deviation. These are called the parameters, which if I know these two things, I can figure out anything else about the distribution. So then let's think about, well, what is that? Let's have a look at an example. If I said, well, I've got a normal distribution called X with a mean of 10 and a standard deviation of 2. And on my graph, I'm going to add that mean of 10. Okay, so put that in there first. And a standard deviation of 2 means if I go up by 2 standard deviations, or go up by 2, that's moving up by 1 standard deviation. And if I go down by 2, I'm going back by 1 standard deviation. So that gives me values of 8 and 12, adding and subtracting 2 from the mean. If I now look at that area, shade that area in, moving 1 standard deviation plus or minus 1 standard deviation from the mean, that covers approximately 68% of my data. Okay, so 68% of the data will lie within 1 standard deviation of the mean. If I go out another standard deviation, so plus 2 and minus 2, that's going to take me out to the values of 6 and 14. So now between those values of 6 and 14, that means we can now talk about how 95% of our data lies within 2 standard deviations of the mean. Then if I go out a third standard deviation, so I'm going plus another 2 minus another 2, between the values of 4 and 6, that is going to cover now that total area between 4 and 6 for the normal distribution with a mean of 10 and standard deviation of 2. That is going to cover approximately 99% of my data lies within 3 standard deviations of the mean. Okay, so now let's just have a look at, think about your number line, and I'm going from 0 up to 60, and then I'm going down to some negative number as well. So I'm just drawing in a number line. I might collect some data about negative numbers, okay, and then I'm going to draw in a normal distribution with those values. Every time I take a sample, I'm going to get a different mean, different standard deviation, and it's going to be more spread out, less spread out as we go along. So what does that tell us? Well, that tells us that there are lots of different means and standard deviations that we can have for different data sets. So there are infinitely many normal distributions. Every time I measure height, weight, age, gender, you name it, anything I measure, it's going to give us different normal distribution. So that leads us to what we need to have as they call it a standard normal distribution. And they're going to use a letter Z to denote our standard normal. And the reason we're going to have this is so that we've got one distribution that we can convert all other distributions to and have a single set of probabilities for. So we'll talk about our normal distribution. So Z is a special one, it's called a standard normal. It has a mean of 0 and a standard deviation of 1. When I draw my graph of that, again, I'm going to put the mean of 0 in the middle, and I'm going to go up 1 standard deviation to the value of 1, up another standard deviation of 1 to the value of 2, up another standard deviation so that's plus and minus. Now I've gone up plus 1, 2, and 3 standard deviations from the mean. Equally, if I go back by 1 standard deviation, back by 2 standard deviations, and back by 3 standard deviations from the mean. Now the areas that are covered under this are the same as what we just talked about under that normal distribution. So there's our mean of 0 and our standard deviation of 1. That's why we're adding and subtracting 1 each time. So let's have a look. If I've got a standard deviation, normal distribution with a mean and some standard deviation, I want to convert that into our z distribution, which has a mean of 0 and a standard deviation of 1. And there's a little formula that does that conversion. Z equals x minus mu over sigma. So x is just a data value. So take away the population mean divided by the population standard deviation. Let's have a look at an example, see what this actually looks like. Okay, so this is an example on page 17 now. So they've got some data about heights, and they tell us that the heights are normally distributed with a mean of 150 centimetres and a standard deviation of 5 centimetres. So I've got my normal distribution drawn up there, and I'm going to add some values onto that. Put the mean in the middle at 150 centimetres. If I add 1 standard deviation above the mean, that's going to take me up to 150 plus that standard deviation of 5 is going to take me up to 155 centimetres. If I go up 2 standard deviations from the mean, then I'm adding on another 5, and that's going to take me up to 160. 3 standard deviations takes me up to 165. If I go back by 1 standard deviation, then I'm going to subtract 5 and go down to 145, down by 2 standard deviations to 140, down by 3 standard deviations to 135. So this, remember, is what we're trying to make equivalent to. We're taking the same graph, and what we want to do is look at, in particular, this value of 160, and recognise that we've gone up by 2 standard deviations from the mean. If I was to convert this using our little formula, x minus mu over sigma, then what I'm going to do is I'm going to end up with 160, which is my data value, subtracting the mean, population mean of 150, divided by the standard deviation of 5, and that's going to give me a value of 2. So this is confirming that we are 2 standard deviations above the mean, and for a z distribution with a mean of 0 and a standard deviation of 1, that gives us our value of 2. Let's have a look at the example now in the book. This is on page 17 again. So what we've got now is we've got the volume of a milk bottle, and it tells us that there is a mean of 1,005 millilitres with a standard deviation of 2 millilitres. So first of all, we're going to draw on our x distribution, put our mean of 1,005 on there, and I usually just tend to write the standard deviation underneath that, just so that it's written down there and I'm not going to lose that data. I'm going to convert this to our z distribution, and we remember our z distribution has a mean of 0 and a standard deviation of 1. Now in the first example, it says to us that we want to investigate this value of 1,008 millilitres. Okay, and you can see I've drawn that on my x distribution on the left. And what we want to do is we want to find the equivalent z value that's the same distance apart on our z distribution. So we start with our formula, z equals x minus mu over sigma. So that's x minus the population mean divided by the standard deviation. So I'm going to put in my values of x, which is 1,008, minus my mean of 1,005, divide by the standard deviation of 2, and that gives me a z value of 3 over 2, which I can convert to 1.5. So that now tells me that from our X distribution, the value of 1008 millilitres is equivalent to the value on our Z distribution of 1.5. And knowing this means we're going to be able to go and find some probabilities with it in a short while. If we look at the second example there, again, I'm just drawing my X distribution with my mean and standard deviation on it. And I'm going to need to convert this to the Z distribution again with a mean of 0 and standard deviation of 1. What we want to do now is convert this value of 1,000 millilitres. So again, I've got my scale along the bottom, so 1,000 is below 1,005, so that's why I've recorded it down below. And I want to find that equivalent Z value in the same position as my X. So with our formula, Z equals X minus the mean over the standard deviation, which means 1,000 millilitres take away 1,005 millilitres over 2 millilitres, and that's going to give us a Z value of negative 5 over 2, which is the same as negative 2.5. So that tells us that the value of 1,000 is 2.5 standard deviations below the mean.